Today's forecast is not something most people will ever read, and yet it may quietly describe one of the most important weather setups forming across the United States this week. It comes from the Weather Prediction Center in a technical document called the Excessive Rainfall Discussion, a briefing designed not for headlines, but for understanding where the atmosphere may exceed the land's ability to handle water. And inside today's discussion is a pattern that deserves serious attention, because it is not describing a single storm, but a multi-layered atmospheric system building across the country. Right now, the United States is entering a highly active weather period where multiple hazards are unfolding at the same time. In one region, severe thunderstorms are developing with the potential for hail, damaging winds, and tornadoes. In another, extremely dry air and strong winds are creating critical fire weather conditions. And in between these two extremes, a third and more subtle threat is forming a deepening moisture-rich environment that could lead to significant flooding in parts of central and southern Texas. To understand how this is developing, we have to look far beyond Texas itself. Thousands of miles away over the tropical Pacific Ocean near the Marshall Islands, a large reservoir of warm, humid air is being drawn into a powerful upper-level jet stream. This jet stream is moving at speeds exceeding 60 knots and is acting like a conveyor belt, transporting moisture across the Pacific Ocean, across Mexico, and directly into the southern United States. This long corridor of atmospheric moisture is what meteorologists refer to as an atmospheric river. It functions like a river in the sky, carrying concentrated water vapor over long distances. While atmospheric rivers are often associated with the western United States, what makes this particular setup notable is its origin and scale. It stretches nearly 6,000 miles, connecting tropical Pacific moisture directly to Texas. As this moisture reaches the southern United States, it is measured in terms of precipitable water, often abbreviated as PW. This value represents the total amount of water vapor contained in a vertical column of the atmosphere. Forecast models are indicating that PW values may exceed 2 inches in parts of Texas later this week, which is considered highly elevated for this region and time of year. When precipitable water values reach this level, the atmosphere becomes capable of producing very heavy rainfall rates. However, rainfall alone does not determine flooding risk. The critical factor is how storms behave once they form, and that is where the current setup becomes more concerning. A slow-moving low-pressure system is expected to move eastward from the southwest into the southern plains. At the same time, a nearly stationary frontal boundary is forecast to set up across Texas, roughly aligned with the Interstate 20 corridor. This boundary will act as a focusing zone for repeated thunderstorm development. When thunderstorms repeatedly form along the same boundary and move over the same region, the process is known as training. It is similar to train cars passing along a single track, one after another, delivering rainfall to the same location repeatedly over time. This is one of the primary mechanisms behind flash flooding events. Central Texas is particularly sensitive to this type of setup because of its geography. The Texas Hill Country is defined by thin soil layers sitting on top of limestone bedrock, combined with steep terrain and narrow river valleys. This type of landscape does not absorb heavy rainfall efficiently. Instead, water runs off rapidly into creeks and rivers. This rapid runoff response is what makes the region part of what meteorologists often refer to as flash flood alley. In these areas, water levels in rivers can rise extremely quickly, sometimes within minutes depending on rainfall intensity upstream. There is historical context that helps illustrate this vulnerability. Past events in this region have shown that under the right atmospheric conditions, rivers like the Guadalupe can rise dramatically in very short periods of time, overwhelming roads, bridges, and low-lying communities before evacuation is possible. It is important to emphasize that forecasting does not guarantee outcomes. Atmospheric systems are highly sensitive, and small changes in storm position or timing can significantly alter rainfall distribution. However, what makes this situation notable is the combination of ingredients coming together at once. Deep tropical moisture, a slow-moving frontal boundary, and repeated thunderstorm development are all aligning within the same general region. This combination increases the potential for localized heavy rainfall, and in some cases, flash flooding where storms repeatedly track over the same areas. At the same time, this system is not isolated to flooding concerns alone. The same environment that supports heavy rainfall is also capable of producing severe thunderstorms. Strong wind shear and atmospheric instability may support storms capable of large hail, damaging winds, and isolated tornadoes. This creates a complex hazard environment where different threats can occur in close proximity. One area may experience severe weather with hail and wind, while another nearby location may experience excessive rainfall and flooding within the same time frame. To the west of this system, conditions are entirely different. Dry air, strong winds, and low humidity are creating elevated fire weather conditions across parts of the southern plains. This contrast highlights the scale of the atmospheric pattern currently in place as we move into Thursday and Friday. The moisture content is expected to peak across Texas. Storms forming along the stationary boundary may become more efficient at producing heavy rainfall, especially if they repeatedly develop over the same corridors. Cinematic weather model display showing Texas with PW values increasing beyond 2 inches, glowing heat map overlays intensifying across the state, digital storm forecasting interface, dramatic newsroom, lighting reflecting on screens, dramatic split scene visualization comparing normal atmospheric moisture versus extreme high precipitable water conditions, showing one side with light clouds and the other with dense saturated storm, clouds capable of heavy rainfall, high contrast scientific style, close-up satellite style animation of storm clouds rapidly developing in a moisture-rich environment, showing intense vertical cloud growth and heavy rainfall cores forming inside cumulonimbus clouds. Cinematic weather simulation look. Wide atmospheric view of a slow-moving, low-pressure system swirling over the southwestern United States, with spiral cloud rotation expanding eastward, pressure lines and wind vectors displayed in a high-detail meteorological map overlay. High-altitude satellite visualization of a nearly stationary frontal boundary stretched across Texas, glowing as a long horizontal line separating warm, moist air and cooler air masses, storm clusters, forming along the boundary. Cinematic weather radar views showing repeated thunderstorm formation along the same frontal line, multiple storm cells appearing one after another over identical locations, illustrating the training effect in real time. Conceptual animation of storm train cars moving along a single invisible track in the sky, each storm cell dropping heavy rainfall over the same geographic region. Rhythmic repetition, dark storm. Clouds and lightning flashes. Aerial view of central Texas landscape during storm setup, showing rural terrain with rivers, highways, and low-lying flood zones under rapidly developing thunderstorm clusters. Dark skies and heavy rain curtains. Detailed cinematic visualization of Texas hill country terrain, showing limestone rock layers beneath thin soil, steep hills, and narrow winding rivers, emphasizing geological structure and flash. Flood vulnerability. Dramatic rainfall runoff simulation over rocky Texas terrain, showing water hitting dry ground and immediately flowing into fast-moving creeks and rivers, highlighting rapid flooding response in steep limestone geography.